Hey guys, welcome. Yeah, so I'm exhausted, but I'm gonna show you how to solve this really neat integral. Yeah, okay, cool. Now to start, notice that x to the power x is equal to e to the power x times ln of x. And yes, I'm not gonna show you like basic algebra details. You should follow. Now, as a series, e to the y is equal to sum n equals 0 to infinity y to the n over n factorial, right? So then, letting y equal x times ln of x, we see that as a series, e to the x ln of x is equal to, n equals 0 to infinity of x to the n times ln of x to the n, like that. And the only thing missing is dividing by n factorial, and I could write that as 1 over n factorial right there, right? Okay, cool. Now, we have integral of x to the x from 0 to 1, right? So that amounts to writing 0 to 1 here, and then a dx right there, right? Monsieur dx. Okay, and so then I need to put an integral right here, but lowercase sigma, the integral sign, and capital sigma can swap places, so I can write integral 0 to 1 right here. Now, a lot of what we're going to do rather in the next 5 minutes or so is going to be dealing with this integral. So let's take mental note that we have this here, which is 1 over n factorial, and then sigma n equals 0 to infinity. But otherwise, because we need the space, let's erase everything but the integral from 0 to 1 of x to the n ln of x to the n dx. Yeah, okay, now we're going to do integration by parts for this integral. So let's write it as 0 to 1, and then ln of x to the n times x to the n dx, like that. Yeah? Okay, cool. Now, for integration by parts, let's let ln of x to the n be u, and therefore let's let this be dv. Okay, now we know the integral of u dv is equal to uv minus integral v du. So the minus integral v du, let's save for a little bit. Let's first work on the uv part. So the uv part, well, we have u is going to say ln of x to the n, that's u. And then based on dv, v is going to be x to the power n plus 1 divided by n plus 1, and this we want to evaluate from 0 to 1. So tired, y'all. Okay, but wait, slow down. We cannot plug in 0 into the natural log of x, right? So we make this fix, this adjustment. Let's write an a there, and then write lim as a goes to 0 here. Now, we first have to plug in 1, and when we plug in 1, this limit as a goes to 0 is not going to affect that part, right? So we just plug in 1, and if we do, we're going to get the natural log of 1, which is 0, to the n, still 0. So we have 0 times, who cares? So when we plug in 1, we get 0, but we have in front of it lim as a goes to 0, right? So this 0 is from plugging in 1. And so we do minus, and now we plug in a. When we plug in a, we get the natural log of a to the power n, right? And this a, let's scoot up higher, right? So a plugged in here gets us that. And then a plugged in here is a to the power n plus 1, which if I so chose, I could write as a to the power n times a. And of course, we have all this divided by n plus 1. Now, I intentionally wrote a to the power n plus 1 as a to the n times a, so that I could use square brackets to group this part like that, because in a video where I provide you an additional example on L'Hopital's rule, I show you that the limit. Jesus, I'm so tired I can't speak. So I'll link that video below this. But yeah, in that video I show you using L'Hopital's rule, really Euler, that the limit is a goes to 0 of the natural log of a to the power n times a to the n is 0. So check out the link to that video, where again I show you limits a goes to 0 of what I have in square brackets here is 0. So we have 0 times, who cares? So in the evaluation here, we get 0 minus 0. Yeah? Okay, because again, this limit is 0. And so this whole thing is 0. Yeah? Okay, cool. So the UV part after evaluating is 0. How convenient, because we need the space. And so now we work on the minus integral v du part. So that's minus integral 0 to 1. V is, as we said earlier, x to the n plus 1 divided by n plus 1, but I left space here so I could write divide by n plus 1 aquí. Yeah? So that's v, and we need du. U, remember, is the natural log of x to the power n. So du is going to start with an n, but I left space here for the n, and then times natural log of x to the power n minus 1, and then by chain rule the derivative of the natural log of x, which is 1 over x, and of course monsieur dx. Right? Okay, now we can clean this up a little bit. Specifically, I can get rid of the 1 over x here and just write x to the n instead of x to the n plus 1, right? Okay. So where to from here? Well, we're going to make the following substitution, which is, let's let t equal the natural log of 1 over x. Notice then that negative t is a natural log of x. So negative t is equal to the natural log of x. And based on that, e to the negative t is equal to x. Right? Furthermore, notice that dt is equal to 1 over x, and then by chain rule times the derivative of 1 over x, which is negative 1 over x squared, and then of course times dx. Right? Now 1 over x is just fancy for x, so I could write an x right here. Right? Now x times negative 1 over x squared is just negative 1 over x, so I could do that. And now I see that negative x times dt is equal to dx. But then I pay attention, so I notice x is e to the negative t. So dx is really negative e to the negative t times dt. Like that, right? Yeah. Okay, so we've got all the pieces to come here and plug in here. Now, dx is negative e to the minus t dt, so the negative in front of e to the minus t we can use to cancel this minus sign, and then the rest of dx is going to be then e to the minus t dt. So tired, can't speak, right? That's the rest of dx. And then x we said is e to the minus t, so x to the n is going to be e to the minus t to the power n, right? And then the natural log of x is negative t, and so we have negative t to the power n minus 1. Now notice then we can write in our next step n over n plus 1, and then also the limits have changed. It's not 0 to 1 anymore, right? Because with this substitution of t, the lower limit 0 turns to, that's x equals 0. So 0 turns to the natural log of 1 over 0. That's like the natural log of infinity, which is infinity. So this lower limit turns to infinity. And then the upper limit, 1, turns to, I'm so tired, 1 turns into t equals the natural log of 1 over 1, which is the natural log of 1, which is 0. Alright. Yeah? Okay, cool. Now, so then we could write this, which is n over n plus 1. Now, here we have e to the minus t to the n, but here we have e to the minus t to the first. So together they make e to the minus t to the power n plus 1, right? And also we could swap the limits of integration here and put a negative right here. And so go to 0 to infinity, right? And I made up for swapping the limits again by putting a negative sign right there. And then as I said, this here and that there combine to e to the minus t to the power n plus 1. And then minus t to the power n minus 1 is negative 1 to the power n minus 1. And then t to the power n minus 1, right? And of course we have dt. Alright, now this minus sign right here, that's really negative 1. So I can incorporate them here. I have negative 1 to the power n minus 1. So if I multiply by negative 1, I can write negative 1 to the power n. Yeah? Okay, cool. Now what? Now this. Well, let's write n over n plus 1 and then negative 1 to the power n, right? And then we have 0 to infinity and then e to the minus t times n plus 1, right? That's the same as e to the minus t to the power n plus 1, simple exponent rules. And then t to the power n minus 1, remember I've pulled out the minus 1 to the n. So t to the power n minus 1 dt. T to the power n minus 1 dt. Man, is this gonna end? Yes. Je suis très fatigué. But yeah, it's like, screw French. Sorry guys about my language. Yeah, okay. So now, what do? Well, now let's make the following substitution. Let's let w equal t times n plus 1. That's the exponent of e here, except for the minus sign, right? Okay, then dw is going to equal n plus 1 dt. So dt is going to equal dw divided by n plus 1, like that, right? Furthermore, t is going to equal w divided by n plus 1, right? And je believe that's everything we need to start substituting, right? Okay, cool. So we go n over n plus 1, negative 1 to the n, 0 to infinity, the limits of integration don't change, and then e to the minus w, right? But then t is w divided by n plus 1, right? So we have w divided by n plus 1 to the power n minus 1, right? And then dt is equal to dw divided by n plus 1. So the n plus 1 here from dt being dw over n plus 1, we can integrate here and write the n plus 1 that was there as n plus 1 squared, and I need the space anyway, and so the rest of dt is just dw. So dw. Right. Okay, so now what? Now we have n over n plus 1 squared, and then integral 0 to infinity e to the minus w, and then w to the power n minus 1 divided by n plus 1 to the power n minus 1. So this n plus 1 in the denominator will have an exponent of n minus 1. But wait, we have an n plus 1 in the denominator here with an exponent of 2. So we can combine them, and instead of a 2 here, write an n plus 1. So I got this n plus 1 because we had an n plus 1 to the power 2, and here we have an n plus 1 to the power n minus 1. Simple exponent rules, right? Okay, dw. But wait, we know, well, I don't know if we know, but I know, that gamma of n, the gamma function, which is on the one hand equal to n minus 1 factorial, is on the other hand equal to the integral from 0 to infinity of e to the minus t, and then it's going to be t to the n minus 1 dt, right? So if this here is gamma of n, then I claim that this here is gamma of n also, because all we have here is, instead of t's, w's, but otherwise this integral here is clearly the same as this integral here. So what I'm saying is all this here is simply n minus 1 factorial. So picking up from here, we have n over n plus 1 to the power n plus 1, right? And then negative 1 to the power n. And then we have gamma of n, which is n minus 1 factorial. But because I'm a fantastic student, I recall that this is the result of our integration by parts work. But in front of the integration by parts, we had abandoned sigma n equals 0 to infinity, and then a 1 over n factorial in front of it. Now look here. I have an n here and an n minus 1 factorial. When we multiply them, they make an n factorial. So I could get rid of this and put an n factorial right there. And then I have 1 over n factorial here in front of sigma that we recall. So we cancel there. And so what we have is sigma n equals 0 to infinity, and then negative 1 to the power n, right, divided by n plus 1 to the power n plus 1. Yeah, cool. So we're basically done. We just have to do a little bit of tidying up work, and that looks like this. Well, just to clean up the sigma expression to say we're done, let's just tidy up, which is, let's make the substitution that k be equal to n plus 1. Then that way, if k is equal to n plus 1, notice that n is equal to k minus 1, right? N is equal to k minus 1. And so then this sigma here, when n is equal to 0, k is going to be 0 plus 1. And so k is going to equal 1. So our final answer is going to be that this here is equal to sigma k equals 1 to infinity, right? But otherwise, n plus 1 is k. So in the denominator, we have k to the power k. And then in the numerator, we have negative 1 to the, well, n is k minus 1. So k minus 1. And done. Yeah? Cool. I hope you enjoyed this. Keep watching. Take care.